All right, let's go through bacterial population growth together because we didn't get a chance to finish this in class. Before we do, you know how important it is to continually quiz yourself. So you've read about the population growth curve, and we've even talked about it a little bit. So what I want you to do is quiz yourself right now. So hit pause on this video and sketch up the number of cells in a closed culture, right, like a localized wound site or a test tube or a colony as a function of time. Go ahead and do that now, and then if you can remember, label all four of the different phases. Ready, go. Okay, presumably you took the time to go ahead and sketch that up, and I bet it looked exactly like this, right? With lag phase down in the bottom left, a log or exponential phase, stationary phase, and then a death or decline phase where the number of viable cells is actually declining. So what I want to do though right now is actually talk about what's happening to the cells in each of these phases, starting with lag phase. When bacteria first find themselves in a new habitat, maybe it's just a few cells that find themselves on the back of your throat, or you get a cut and it's a few Staph aureus cells that find themselves in the cut, or when we inoculate, right, a colony-forming unit finding itself all alone sitting on a petri dish. Whereas before it was maybe frozen, it was in the fridge, it was on a door handle, it was someplace where it was probably in stationary phase, realistically. So what happens when the bacteria find themselves in a new habitat? Well, when they're in this new habitat, they begin sensing their environment. The cell membrane, and in the case of gram-negatives, the periplasm, are just loaded with sensing proteins. They're sensing everything from sugars to oxygen to pH. And what they do then is send signals to the inside and access their genome, access their DNA, to create a proteome, a collection of proteins, that best takes advantage of the available resources. Now, if things are missing, they may just say, hey, we got to stay here in lag phase and not try growing because there's no oxygen or there's no glucose, there's no amino acid or whatever it happens to be. But if they've got all they need, then they're going to go ahead and begin growing. But that lag phase can take a while as they're sensing, or it can be extremely short. It can be almost instantaneous if the last habitat they were in is identical to the new one. So they were already growing, they'd already geared up for those conditions, and now they find themselves in the same conditions, though maybe with more of everything, more available oxygen and nutrients and so on. All right, so presumably our happy little cell or cells have gotten out of lag phase. They're all ready, they've produced the best proteome they can for the conditions. They're then going to begin growing and dividing the fastest they can. So we say that the cells are optimized for growth under the conditions present, and we say that the numbers are increasing by a constant normalized rate. And what we mean by a normalized rate is how long it takes one cell to become two. So if you open up your book and you take a look at the figure that shows binary fission, going from the first step to the last step, from one cell to two, before those two cells are ready to go ahead and divide again, how much time that takes. And that ranges, right? People make the claim that E. coli under perfect conditions can double every 20 minutes. I've never been able to reproduce that, but I can get E. coli to grow every 30 minutes, double every 30 minutes. And in an infection, it's probably more in the order of hours rather than minutes under most conditions. Excuse me. So the normalized rate is constant, right? It's how long it takes for them to double. But their absolute population growth rate is always increasing, right? If you don't believe me, think about the problem I gave you a few days ago, where we started with 1,000 cells, and after 1 hour, we had 2,000 cells. So we increased by 1,000 cells per hour at the beginning. But late in the game, we're doubling still every hour, right? So we're going from 1 million to 2 million. Now we're increasing by 1 million cells per hour instead of 1,000 cells per hour. So the absolute growth rate is always increasing as the population size is increasing, even though the normalized or per cell growth rate, the doubling time, is staying constant. Now, some of you are staring at your screen and wondering what the heck I just said. If you need to pause right now, go to the textbook, read about it a little bit, think about it more, bring questions to class if you're stuck. Now, eventually, in a closed system, and what I mean by a closed system is no new nutrients are being brought in and waste products are not being removed, that closed system is going to have a capacity, right? A flask can't hold an infinite number of cells. It can't. The nutrients that are there are eventually going to run out, and waste products are eventually going to build up. And when that happens, whether it's in a flask or a test tube or a colony on a plate or an infection, in your cutaneous layer, then the cells are going to enter stationary phase, where there's no net increase or decrease in cell numbers. You may have a couple cells die, but if a couple cells die, their raw materials, their biomass gets recycled and a couple cells are born. Okay, so our population size remains stationary, and that's where the name comes from. The cells can continue to function. Their function might be a little altered. In some cases, bacteria will only produce toxins in log phase, but not in stationary phase. In a few rare cases, we've seen that toxins are only produced in stationary phase. That's less common. So their metabolism may be altered a little bit, but they do continue to function. The growth is limited or halted due to two things, either or, whichever one hit first. Resource availability. So some resource became limiting. It ran out. It got too low to support any further growth. Or waste accumulation. Under most circumstances, it appears that stationary phase is reached because of resource availability, and that death phase is most often triggered as wastes accumulate to a point where the cells begin taking on irreversible damage. And that's our last slide here. Death phase, it's where the death rate begins to outpace any division rate. So maybe you have 2 cells die and only 1 new cell is born, or 200 cells die and only 10 new cells are born, and so on. There may still be some resources available, but chances are if you've pushed through stationary phase, you've depleted something, some key nutrient that is now limiting. And waste accumulation at this point becomes the limiting factor, because wastes can be chemically toxic to the cell, and they can actually begin causing irreversible damage. All right, so I want you to go back through this a couple of times until you're comfortable with it. And I want you to try that sketch again a couple of times and make sure that you're able to pull this off. All right, I hope that was helpful for you.